touch these buttons, or I can scroll it, depending on what I'm familiar. For me to keep. Okay, and it goes in here. I'm Craig Burton, I'm the head of the electronic voting project, and you're now in our IT department. You can hear other people around you. It's a working IT department, and we're in the middle of the election. And what we've got together today to do is witness what I call the decryption ceremony. And the decryption ceremony is a step in the electronic voting process towards the end. And so today what I'm going to do is talk briefly about this setup. Then I'm going to start it. The actual process runs for maybe 20 minutes, and then while the system is running, I'll give you a more detailed explanation of technically what's going on, and I'll also describe the security of the system. So first off, the people who assembled to see this process are the election stakeholders, the election operations people, and any other observers or international observers who want to come together to witness this important step in the process. And it's really part of the transparency of this design of electronic voting. Now, the stage that we're at is that all the votes have been collected. There's 1,121 votes, and they were all collected last week, and they're all in a machine behind you. So just behind, over there, there's seven servers in a machine rack. They have collected what we call receipts. And these machines here, their job is to cooperatively decrypt those receipts back into votes so that we can count them. And the equipment, as you can see, is 5 laptops. They're not connected to the LAN, they are talking to each other. This guy here is what we call the console, so his job is to tell these guys here what to do. He hands out work packets for them, and they shuffle them, and they decrypt them. So it's a little bit like in the paper election where we get a ballot box, and we shake it, cut the seals on the box, and then empty out the votes. This is the electronic equivalent of that. The problem with electronic voting is that it's much, much harder to do shuffling in a way that can't be undone. And so this is why you have this many machines working very hard. So now what I'm going to do is I'm actually going to start this process, and then while it's running, and you'll see it progressing over here, I'll talk more about this ceremony, the machines, and then what will come out the end of this process. Okay, so starting the process off is very easy. I just basically turn on each of these shuffle and decryption nodes. So I'll start this guy here. Okay, so really they're all the same, right? So I just move along. I'm just telling each single machine to start work. Okay, and then I come over here and I start up a console. And I wait for the console to come up. So here I am, I'm just going to answer a few questions on here, such as input files. The input files are of course the receipts. It wants an output directory, and I'll explain what that's for in a minute. Now the system asks me for a shuffle plan. These machines, any one of these machines could break down, and if it did, you could imagine we wouldn't be able to decrypt the votes. So the way it works is only 4 of these 5 need to be working, and here's where I tell the console that we've got all 5 present, or perhaps we were missing node B. This is how I would tell the console. Okay. And then I tell it the configuration of this specific election. Okay, and I upload the votes. So this takes about 2 minutes, and what the console's doing is he has all the election receipts from the servers. I brought them over on a stick, and he's putting some of them on each of these machines. And then these machines will shuffle them among themselves, and then it's a threshold decryption scheme. They'll agree and decrypt. So it's uploading. It's got about another minute to go, and then I'll kick it off. While it's doing that, I'm going to say something about this particular collection of machines. You might notice that they are all Dells. They're all Dell Latitude laptops, all exactly the same, and they are all running the same software. Okay, this is actually a concession that we made in 2014. The final design of this system is much more secure and private if each of these machines is different, so perhaps a Dell, an Apple, whatever, but also the software running on them should be an independent implementation of the MIX protocol. So in fact, we don't actually care what the software is. What we care about is that there are services on each machine obeying a protocol. Okay, so that's where we want to go longer term. And what's interesting about this is that each machine should not be kept here together at the VEC. Okay, I kept all these machines here in a safe. In fact, they should be tossed out to the world. They should be given to another commission. One could go to a political party, whatever, right? All spread out in the world. And that provides us with a kind of disaster recovery. Okay, that provides us with more resilience. But also, we don't want these machines to collude. So by handing them out to different organizations, especially organizations who are mutually distrusting, we can be sure that these machines aren't brought together prematurely. They aren't used together to decrypt receipts before this ceremony. Okay, so our ceremony today is a little bit artificial, but it's happening anyway because we need to demonstrate how this works. Okay, so it's almost finished doing the upload. I can also say that the 7 servers in there are all running an application called Suvo. And again, each one of these 7 servers is the same. In an ideal scenario, you wouldn't have 7 machines together in the machine room. You'd have a heterogeneous implementation out there in the world. So you might have one of these servers again with a political party, one of these servers in the cloud, one of these servers in Canberra. And so when a voter goes to vote, his receipt is collected by these machines spread out around the country, each one running an independently developed version of the software. Okay. An obvious advantage is that imagine if there was a bug in this mixing software here. Every one of these laptops would have the same bug. Do you see? Whereas if there were independent implementations, a bug might take out one of them, the others could still do a good shuffle and a good decrypt. Right. That's a likely scenario. Bugs are the biggest problem we have. Okay, so the system has uploaded. So now I go over here and I dismiss it. I choose all the races to decrypt in one go. I could actually pick just the races where we need the results quickly. So if there were some very close contested races in this election, I would go and pick those ones and do it first so that it gets done first. Instead, I just grab the lot and I click go. Okay. And so the machine is just now going to tell these guys to start working, and then it sits there and it collects the results of what they hand back. Now what they're doing at the moment is they're swapping individual receipts around among themselves. Then they decrypt them, and when they decrypt a receipt, what they get out the other end is just a plain text vote. Okay, so it's a comma separated variable file. You can see it in a spreadsheet, and it's basically the voter preferences in legal order. So what I'll explain now is really what's going on here. In conventional electronic voting, if you come in to vote, I take your vote and I encrypt it for you. And if you want any kind of proof of what I've done for you, all I can do is sort of say, well, here's the encrypted vote, and it's just garble. Okay, so you vote in our system, I encrypt it, it turns into an enciphered message. It's just garble, and you can't see what it is and you can't decrypt it. What's actually happening in this design? This design is an implementation of pret-a-vote. Now this might look a bit like garble as well, but in fact this is what we've captured. And you can actually see the elector's preferences here, because this is a JSON structure, and one of the entities in the structure is actually the elector preferences. So the elector preferences are actually world readable, even though the vote is encrypted. And the way it works is that in Melbourne, and when we vote here, it's a preferential system. So you must number your candidates in order. So if you can imagine a ballot with a list of names, let's just pretend I numbered my names 1, 2, 3, 4, 5. Okay, that's my choice. Notice here that my vote, I've highlighted a 5. Okay, so even though I put a number 1 in the topmost position, this is my receipt here, and it's put a 5 in the topmost position. This is the encryption. So instead of encrypting my vote into just one giant blob, the way Suvote works is it actually encrypts the individual ballot positions. Okay, so the individual ballot positions are shuffled and encrypted. I can illustrate this a bit more clearly when I show you what it is we give our electors. Okay. If you were one of the electors who voted in Victoria, or you voted in London, once you were marked off the roll, you would have been given one of these. Now we call this a candidate list. It's actually the candidate names part of the pret-a-vote ballot. And this is just a list of all the people I can vote for. That's all it is. However, the order of these people is randomized. Okay? So in this particular ballot, I've got Francis Alberton first. He probably isn't first in the legal order. And furthermore, a guy behind me in the line, in the voting place, would get a different order to me. And the order is a secret. Okay, I'm allowed to see this order, and this order is something I can check in the polling station only. And when I vote on a tablet computer, and I just see the legal ballot. Okay, we are only allowed to show electors the legal ballot. We can't scramble the candidate order. When I finish voting, the system prints out my preferences. Now remember how I said I actually voted 1, 2, 3, 4, 5 on the screen? So I gave the top guy on the ballot, on the legal ballot, my 1, and I went down in order. This list here is not 1, 2, 3, 4, 5, as you can see, because it's got to match this shuffled order here. In fact, I put Stephen Albany first. When I look up my 1 here, it's next to Stephen Albany. Okay? And I gave Katie Blakey my second preference, and lo and behold, here she is. So you can think of this as a kind of a code sheet, and I use this code sheet to just check my encrypted vote is correct. That's its purpose. When I'm happy with this, this stays behind in the polling station. This is securely destroyed so that nobody else has my code sheet. Okay, so this is destroyed. And it is this that we collect centrally. And it is this that is made public and that the voter can take home. And it's this, and everything on here, everything on the long receipt is what you see here on the A4 sheet. It's all the same information. And that includes some signatures. So if I leave the polling station and I am not so sure that the VEC actually got my preferences, I can scan this with a QR code. There's an Android application on the Play Store which can scan this QR code. It has the election public key, and it can say for certain these preferences were captured 3 blank 7 5 1 6 4. The Electoral Commission got these preferences in their shuffled order. And again, what these machines here are actually doing is they're just decrypting what that shuffle is. And once the shuffled order is known, these machines rearrange my preferences. In this case, they're going to put my preferences back into 1, 2, 3, 4, 5. And then my vote will be counted. Okay, so just to explain that again, perhaps I'll explain it a little bit more technically. Previously I said that older e-voting systems just encrypt messages, and they might just use something like RSA encryption. In that circumstance, one machine decrypts. Okay? You might have a fancy arrangement where I split up the password for that machine and I split it up with you. But in the end, those two pieces of the password have to come together. And so the machine learns the password, and the passwords would have been generated on one machine, and one machine knows everything. It's too much. In this circumstance, there's no password. Okay? There's only 5 private keys, and they all cooperate to decrypt an elliptic curve point. So elliptic curve cryptography is a kind of cryptography where separate machines really can separately, cooperatively decrypt things. Anything else, such as with RSA encryption, at the end of the day it's one machine. Okay, only one machine can use one key to decrypt one message. This design, it really can take 5 machines or 7 machines, as many as you want. They all have to cooperate. And that's very important because the trust that you place in these machines can be spread out. The burden of trust can be spread out among several people. The problem with conventional e-voting is that eventually there's 3 geeks or 2 geeks that have access to the machines. And they have to have access because they have to maintain them. What we really want to do here is spread out the IT load so that there's like a geek a machine. And furthermore, they don't collude. So, of course we need technical support for this, right? But we need it in a way that doesn't put IT staff at risk. Alright. So what comes out the end of this process? Okay, I can see over here that we're approaching the halfway mark. Because the e-voting is only a small component of this election, so this election took 3.9 million votes. I've only got 1,121 votes here. It means they can't be e-counted. So instead what will happen is that these machines will produce CSVs, comma-separated variables, and we convert those into PDFs. So this is a PDF of one of our votes. And you might say, well, gosh, how do you know that the PDF process doesn't break the votes? Okay, PDF software is very complex. And we have a low-tech answer to that. Every one of these printed out votes has a footer, and the footer has a number which aligns with the row of the CSV file created. For example, this vote here is the 2nd row of the CSV file that was emitted by the mix. So this means we can do quite simple spot audits at at voting locations. So when we give them their printed votes to count, they can do a quick spot audit. They know they've got our votes, and they know these votes match the CSV files. So another good thing about this design is that it emits proofs. And so there is quite a lot of risk with computers that bits drop off here and there. It's very easy for computers to damage information. Therefore, it's very desirable for each of these machines to prove that they each performed in the shuffle. None of them added votes, none of them removed votes, and none of them damaged votes. And so each of these machines emits a shuffle proof, and these proofs are made public. The proofs are quite simple. Each one of these machines actually does 2 shuffles. They do what we call an in shuffle and an out shuffle. And so you can imagine that a vote arrives in one permutation and it leaves in another. Okay, so this is the shuffle. The votes are being moved around inside their files. Each machine can expose or make public half of the shuffles it performed without giving away the order that it created. So each one creates a new order for the votes inside the file. We can always give out half of the input shuffles and half of the output shuffles, as long as you can't trace one vote all the way through the system. And so that's the purpose of 2 shuffles per machine. And we make these proofs public. We make the receipts public, and we make the votes public, and anyone who goes to the VEC website from this week can actually download all the proofs and the votes and run a verification check. Now, I'll make one more comment about this. The MixNet running on here is brand new. there's a lot of mention of mixed nets in the literature, but when we came to implement the design in the public domain, there was no mixed net for us that we could use. Okay, we wanted an open source mixed net, we had to write it. The same goes for the software that does the vote collection in the server room. There's a lot of references to web bulletin boards, write once web bulletin boards in the literature. When the time came to actually use one, we couldn't find one, so we had to write it. It's also true for our verification software. If you download the VEX, the Electoral Commission's proofs, you'll also get our proof checker. Longer term, you can see it would actually be better if the proof checker was written by somebody else. Okay, someone at arm's length from the project. We couldn't solve all these problems in one go. Okay, so we're about 66% of the way through. You may wonder how on earth we could do a full-scale election if it takes us 20 minutes to do 1,100 votes. In fact, there's quite a lot of overhead in managing these files. Each file only has a few votes in it. The system has been built, and the server system in there has been built to handle 1 million votes. That was a very important requirement, because otherwise, if we hadn't built the system to scale, then it would be a toy. And then in the future, if the Commission wanted to use this at a greater scale, they'd find themselves having to do big rewrites. We wanted to avoid that. So the process has come to a conclusion, it's ended. It doesn't show much more than this progress bar, but it's completed. And what the system is going to do is provide us with CSV files. They'll be batch converted into PDFs, and then we're going to print them all out. And those printed out votes are included with the postal votes. So a certain number of votes are counted on the evening of the election, but then quite a large number, about 1.3 million votes, about a third of all the votes, are counted starting this week when those votes are sent out to the voting locations. So our e-votes will go out to Doncaster, out to Eltham, and they'll be counted along with all the postal votes and the early votes. And it'll take us a couple of hours to do the printing. Obviously, longer term, if you had a majority of votes being taken electronically, the job would flip, and the task then would be to key in the residual paper votes. So longer term, that's how it would work. One of the benefits of this approach and of this system is that it's providing enough public information so that if there's any trouble or any challenges, the information is there. Some of the audits and some of the challenges you can do to this system are very simple, such as comparing the lists, but using the verifier, examining the proofs, this is an expert task. The point is that it's available and it's possible. A problem with conventional e-voting is that if a case ends up in court, the system disintegrates down to arguing about log files, arguing about things people said and saw, or arguing about the quality of the software being implemented, for example. Saying we got it tested by NASA or whatever. That's not really relevant. Okay, what matters is the integrity of the election being able to be measured independently. So in a large part, what actually goes on here is irrelevant. It's the proofs that come out of the system, the availability of information, and the special design of the system that shifts responsibility into verification, away from software. And you might say, well, that's still a very highly technical task. The point is that if there is a challenge, the Commission has done its homework. And people can, on their own, experts, interested parties can on their own, go and satisfy themselves of the integrity of the election on their own. There's enough stuff out there that's self-evident for them to do that. So I'll now unload the CSV files off this machine, and then they'll be batch processed and printed out pretty conventionally so that they end up looking like this. And if anyone who sees this video has any questions for me, do my best to answer them by email. The email address to use is called codereview@vec.vic.gov.au, code review. And that's our public email address for this project and for verification. If I had your brain, you could make me insane.